Good afternoon and welcome to Computer Science 221. Moving right along in Chapter 10. This is our last chapter. And this is our second to last section that we're going to talk about. And here we're going to be talking about interrupts. And again, actually a lot of what I'm going to be talking about today is review. The first thing I would like you to recall is a very, very long time ago, we gave a very simple execution cycle of a computer. And we basically said that the instruction register gets loaded with whatever instruction is referenced by the PC. And then we said that the PC gets incremented by 1. And then we execute the instruction register. And this was the basic cycle of what occurred here. We are going to slightly modify this picture here. And I want to say at this point, I'll repeat this a couple of times as we go through this. What I'm presenting here in this section is a little bit of how your author has presented it, and I am throwing my own opinions and interpretations in there. You should read the chapter. You'll see that what I've done here is slightly different than what your author has done, but the point is the same. And a lot of these concepts that we're encountering here, you will see again when you take a class in operating systems. Now, this is normally the flow of an executing program. But we said, imagine that you're sitting there, and you're going to get an example of my very bad artistic abilities here. Here's your laptop computer. And here's a running program over here. So what your program is doing is it's continually going through this loop over here. And over here, here's the keyboard. And here are a bunch of keys. And you're sitting here, and you're a very impatient person, and you're pounding the keyboard. Pounding the keyboard. Now, maybe you're pounding it for fun. Maybe you're tapping out a tune. Maybe what you're doing is anticipating that at some point this program may ask you for some keystrokes, and you already know it's going to ask you for that, so you're typing ahead. But right now this program is running and it's doing whatever it is that it's doing. Now, at some point later on, the program may stop, and you'll notice that you'll start seeing the keys down here that you typed in. Now, these appeared here, but they could be a minute after you actually typed them in over here. So what is going on here is when you hit the keyboard, an interrupt occurred. So what does that mean? Well, it means that an alarm went off. In other words, there was a signal to the CPU, hey CPU, you better stop what you're doing because I have something very important for you to do. Well, what is it? Well, first of all, let's understand what's going on over here. Someplace inside of computer memory, there is something called a keyboard buffer. And it's a very finite spot of memory. And who knows how big it is. Maybe it can hold 5 keystrokes, maybe it can hold 10 or 20. And you could think of this, this is getting into advanced data structures, it's a queue. And what happens is you start hitting in these letters in here. So you start hitting in an A. So here's the front of the queue and here's the back of the queue. And now you type in a B, and now this thing goes over here to that. And this thing goes over here to C, and now it comes over there to that. And you're typing in these letters. And you're in some situation like that. Now what happens is your program, so what's happening here, by the way, these are getting filled up every time you pounded the keys. So in other words, your program is up here, and maybe this is Flight Simulator, you're having some fun. And now what happens is you start pounding the keys. What happens is we interrupt the flow of this execution here to go read the keyboard buffer, or to go read the keystroke. We have to see what keystroke was read, and we read it into this buffer. So seeing which key was read and reading it into the buffer, that is what the interrupt service routine does. Sometimes referred to as an ISR. Okay? Now there are lots of ISRs in a computer. There could be one for every time you hit the keystroke. There could be one every time you click the mouse. There could be one every time you move the mouse. There could be one every time some information comes in over the internet. So there are a lot of these different interrupts going on. And what I want to do is I want to revise this program over here. What's going to happen now is we're going to say that the instruction register gets PC of memory. The PC gets PC plus 1. Okay? We come over here and we execute the IR. And here's where things get a little bit different. We ask a question. Did an interrupt occur? Interrupt occur. And if the answer is no, then we just go back over here and we keep executing. Now if the answer is yes, a lot of magic happens over here. Okay? The first thing that we have to do, I'm going to say, who caused the interrupt? Okay, and that's actually going to correspond probably to a number. We'll look at that in more detail in a second. The other thing we have to do is we have to save the state of the machine. Save machine state. Then the next thing we have to do, we're going to run out of space here, is we have to execute appropriate interrupt routine. Okay, then what we have to do is we have to restore the state of the machine. And I'll explain that in a moment. And then when we're done with that, we go and we pick up on our merry way again back over here. Okay, let's take this thing apart in a couple of different ways. Now, first of all, I want you to imagine, here's our CPU chip. Okay, you've all seen these chips. And maybe over here, I'm going to call that interrupt 0. And that's connected to the keyboard. And maybe over here, this is interrupt 1. And maybe that's a mouse click. And let's suppose over here is interrupt 2. And what could interrupt 2 be? Maybe that's a mouse roll, meaning that we scrolled the mouse, or we rolled the mouse on the tabletop. And maybe over here we have interrupt 3. And what could interrupt 3 be? Maybe that's internet input. Okay, let's keep it simple. So there are these 4 different lines over here, okay? And what happens is you could imagine that each one of these lines gets fed into a big OR gate. Okay, so what happens is that there's a 1 that comes out of here whenever any one of these lines goes high. So when we come over here and we're asking the question, did an interrupt occur? That's the same thing as asking, was there a 0 or a 1 coming out of this line? Okay, if there's a 0 coming out of this line, there was no interrupt, and we just continue on our execution on there. If there's a 1 on this line, okay, then the answer is yes, and now we have to come down here and we have to determine who caused the interrupt. Okay, now the way that we would determine who caused the interrupt is now perhaps what we would do is we would come over here and we would poll these lines. Now, is it possible that more than one line could be high? It absolutely could be. Remember, what's coming in here is a 0 or 1. If there's a 1 here, that means the keyboard, that means somebody pounded on the keyboard. If there's a 1 over here, that means somebody clicked the mouse. So these are all interrupts, and there's a very important thing to keep in mind here. The order in which we poll these lines determines which one we're going to service. For the moment, why don't we assume that only one of these has gotten triggered, and we'll return to the case of multiple interrupts occurring a little later on. But let us suppose for the second that somebody clicked on the mouse. Or, I'm sorry, somebody hit the keyboard. Somebody over here struck a key. So an interrupt occurred, we're over here. Who caused it? We went through here and we polled the pins. So I'm going to go over here and I'm going to go, who caused it? And I'm going to say we're going to poll the pins to determine who caused it. And now what we're going to do, okay, so the interrupt occurred on pin 0. Okay, it was interrupt 0. Now, over here, there's something very important to notice. I say I have to save the state of the machine. And here's what I want you to imagine. I want you to imagine, here's my regularly executing program. Okay, remember we said we were playing Flight Simulator or something like that. And here's my program, and maybe at some point we say something like add R1, R2, R3, and then we say branch 0 to here. And let us assume that it is in between these two statements that an interrupt is detected. Okay, so here's the thing that you have to remember. Between these two lines of code, we're going to jump someplace else into computer memory, and we have to figure out where that is, and we'll do that in a moment. But we're going to be executing some other code. And when we're done with all that code, we're going to be coming back over here. When we're coming back over here, we're going to be doing a branch on 0. Okay, now remember, this statement over here is all dependent upon how the flags are set. Now, the flags could have been changed in our interrupt routine. So when I talk about saving the state of the machine, save the state of the machine, what does that mean? Well, it means saving enough information so that when I'm done with the interrupt surface routine, I can successfully come back here and start executing where I left off before. Well, we see that the flags are very important. So one of the things that this means is it means that I need to save the flags. Now, your author even takes this a step further. And your author says that there is something called a processor status register. And actually the flags are part of the processor status register. So there's the zero, there's the zero, there's the negative, and there's the positive. And there's other information in here too. And he talks about in here, there are things about priorities and stuff like that that I'm not necessarily very concerned with. But what we need to do is so this is called the PSR. And your author says you need to save the PSR. I just say, for now, we need to save the flags, but saving the flags and saving the PSR are basically the same thing. Now, the other thing that we need to do is we need to save the PC. Why? Because remember, when the interrupt occurred, the PC was pointing here. Okay? And what's going to happen is we're actually going to, between here and here, we're going to jump someplace else in memory, start executing some other code, and then we're going to be coming back. We've got this. Here's memory. And over here, I'm saying add R1, R2, R3. That's happening here. And then over here, I'm saying branch 0 to some label. But between here, and maybe this is at location 3011, 3012, down here someplace is my keyboard interrupt surface routine. So what's going to happen is between these two statements, I'm going to jump down to here. I'm going to execute all of this. And when I'm done with all of this, I want to come back over here. Okay? So what I need to do, remember, if the interrupt occurred after I executed this statement, the PC is going to contain 3012 on it. So what I'm going to do, or here's the big thing, this is what ties this whole chapter together, there is something called a system stack. And that is somewhere in memory, okay? And basically what happens is when the interrupt occurs, I need to push the processor status register, and I need to push the PC. And these both get pushed onto this system stack. Okay? So that's called saving the state of the machine. Now, where do I go? And what we do is we have to remember a couple of things about the LC3 memory. You may recall that we said way up here at the beginning of memory, from 000 through 0 through 00FF, This was called the trap vector table. Well, there are some more important things here. From 0, 1, 0, 0, all the way up to 0, 1, F, F. This is called the interrupt vector table. And here's where I'm making up my own rules as opposed to what your author did. I will take the interrupt number and to that I will add hex 0, 1, 0, 0, and that gets me a number in the interrupt vector table. So if I come over here, if I generate interrupt 0, and remember we said that the keyboard, that was interrupt 0. So I go 0 plus 0, 1, 0, 0 is equal to hex 0, 1, 0, 0. I come over to here, and this has the address of the interrupt surface routine. For the KBD. Okay? So now, what do I do with this number right here? This number gets loaded into the PC. So again, let's take another So here's hex 0, 1, 0, 0. And this has some number in it. I don't know what number's in it. 0, 4, 30. So in other words, this is the PC gets loaded with memory of the interrupt number plus 0, 1, 0, 0. So in this case, it would be 430. And so what happens now is I come down here to 0, 4, 30, and here's the code for the keyboard interrupt. Is in here. Okay? Now, one new instruction to learn about is down here, there's a new instruction, which is RTI, return from interrupt. Okay, and that's very much like a return statement. Okay, but remember what a return statement did. A return statement just said, take the contents of register R7 and put it back into the PC. This actually does something different. What this is going to do, you may recall that when we saved the state of the machine, we first said push the PSR and then push the PC. Okay, what we're going to do over here is we're going to pop them. So what we need to do is we need to pop the PC, and then we're going to pop the PSR. Okay? I want you all to listen up closely. There's going to be a homework problem because I've just told you something that is incorrect. And I'm going to ask you, why is it incorrect and what do you need to do to fix it? But remember what's going on here. This is getting us our return address, and it's also returning the state of the flags the way it was before. So that when we come over here now, when we come back here, we're going to be doing this branch 0 based on the state of the flags that occurred after I did this add instruction right over here. So the other thing to keep in mind here, and I am almost done, I think I need one more slide here. our view of memory is getting pretty complicated. Here's memory. So over here from 0, 0, 0, 0 to 0, 0, F, F, this is the trap vector table. Over here from 0, 1, 0, 0 to 0, 1, F, F, this is the interrupt vector table. We know a couple of other things. We know that when we learned about doing I/O on these things, that it was someplace in here. Here's where the code was. A lot of code for traps and interrupts. Typically starting over here at 3000, this is where we would start the user program. We know way up here in FF land, we know there's memory over here for memory mapped I/O. Okay, there are other things that need to be in here, and who knows where they are. Someplace, I'm going to say somewhere, there's something called a system stack. Okay, and then somewhere there's something called a user stack. And again, if you read your book, which I hope you all do, this gets kind of complicated. Because you remember when we talked about stacks, we talked about using R6 as a stack pointer. And so we're going to be using R6 as a stack pointer for two different stacks. That's kind of messy. How does that work? Well, it turns out your computer actually operates in two different modes. Okay, there's something called supervisor mode. And there's something called user mode. And each one of these has their own stacks. When you're running a program, when you're writing a Java program, you have a stack that is allocated just for your program. And that is completely different than the system stack, which would be used when you invoke, when you hit the keyboard and you've actually generated an interrupt. These are different things. So the question is how do these two things both use the same stack pointer? And the answer is they both have to, when an interrupt occurs, basically when an interrupt occurs, we're going from user mode into supervisor mode, okay? So one of the things that we have to do is we have to save the contents of the stack, the user stack pointer, onto the supervisor stack, and then we have to get the address of the supervisor stack off of the supervisor mode stack into the R6. It's a complicated dance here. I do ask you to read this over in your book, but the specifics of this are probably left better for a class in operating systems. So I want to go all the way back to our very first drawing here, because I think we've gone full circle here. Okay, so we said, does an interrupt occur? We check the output. We have all these interrupt lines going into an OR gate. If there's a 1 coming out of here, the answer is yes. And that means we have to start going down this branch instead of cycling back. What caused the interrupt? I say we're going to pull the various pins that are hooked up, okay, to interrupt lines. Okay, then we have to save the state of the machine. Saving the state of the machine, we said, involved saving the processor status register, which contained the flags, and we also had to save the program counter. So we knew where we were going to return to when the interrupt was done. Then what we would do is we would take the interrupt pin number, and to that we would add hex 0100, and that would get us an offset into the interrupt vector table, and then we would use that and load that into the PC, which would execute the appropriate interrupt routine. Once we're done with the interrupt routine, we would execute an RTI, return from interrupt. That would pop the system stack. What would get popped off of the system stack? The processor status register will get popped off, restoring the flags to their original state, and we would also pop off the PC, which would allow us to then come back to the proper instruction over here to execute next. How cool is that? Time for rest.